Welcome to our first section on Introduction to Boolean Algebra. Boolean algebra is a branch of mathematics that uses truth values, usually true and false, which we often represent as 1 and 0 respectively. It's fundamental to digital electronics, dealing with logical operations like AND, OR, and NOT. These operations are like the building blocks of digital circuits. Boolean expressions can be complex and lengthy, making them difficult to analyze and optimize. That's where Karnaugh maps, often shortened to K-maps, come in. K-maps simplify these expressions, making them easier to understand and implement in circuits. Imagine designing a digital circuit with multiple inputs and outputs. The logic controlling this circuit can quickly become intricate. K-maps provide a visual way to simplify this logic. This simplification is crucial for efficient circuit design. By representing Boolean expressions visually, K-maps help us identify patterns. These patterns allow us to reduce complex expressions into simpler forms. This simplification reduces the number of logic gates needed in a circuit. Fewer gates mean lower cost, less power consumption, and faster circuits. Now, let's dive into Section 2, Karnaugh Maps, a visual tool. A Karnaugh map, or K-map, is a graphical method used for simplifying Boolean algebra expressions. It provides a visual representation of the truth table of a function. This visual aid makes it easier to see relationships between inputs and outputs. K-maps are especially useful for functions with up to 6 variables, but they become increasingly complex with more variables. The map consists of cells, each representing a possible combination of input values. The arrangement of cells follows gray code, which is a binary numeral system where 2 successive values differ in only 1 bit. This arrangement ensures that adjacent cells represent input combinations that differ by only 1 variable. This adjacency is crucial as it allows us to visually identify groups of 1s or 0s, representing minterms or maxterms. These groups help us derive a simplified Boolean expression for the function. The visual nature of K-maps makes them an intuitive tool for simplification. Moving on to Section 3, Constructing Karnaugh Maps. In this section, we will delve into the step-by-step process of creating Karnaugh maps, also known as K-maps, which are essential tools in simplifying Boolean functions and minimizing logic circuits. To construct a K-map, we first determine the number of variables in the Boolean function. This is a crucial step because the number of variables directly influences the size of the K-map. For example, if we have a Boolean function with 3 variables, we need to prepare for a more complex map compared to a function with just 2 variables. A function with n variables requires a 2 to the power of n cell K-map. For instance, a 3-variable function needs a map with 2 to the power of 3, which equals 8 cells. This exponential growth means that as the number of variables increases, the K-map becomes significantly larger and more complex. Each cell in the K-map corresponds to a unique combination of input values. These combinations represent all possible states of the variables, ensuring that every potential scenario is accounted for in the map. This comprehensive approach allows for a thorough analysis and simplification of the Boolean function. We label the rows and columns with input variable combinations, following gray code to ensure only 1 variable changes between adjacent cells. Gray code is particularly useful because it minimizes the chance of errors during the simplification process by ensuring that only 1 bit changes at a time. Next, we fill the K-map based on the truth table or the given Boolean expression. This step involves transferring the output values from the truth table into the corresponding cells of the K-map. It's a meticulous process that requires careful attention to detail to ensure accuracy. If an input combination results in a 1 output, we place a 1 in the corresponding cell. This indicates that the specific combination of variables produces a true result in the Boolean function. If it results in a 0 output, we either leave the cell blank or fill it with a 0. This step is equally important as it helps in identifying which combinations do not satisfy the Boolean function. Consider a simple example with 2 variables, A and B. This will help us understand the basic principles of constructing and filling a K-map without the complexity of additional variables. The K-map will have 2 to the power of 2, which equals 4 cells. This smaller map is easier to manage and serves as a good starting point for beginners. Let's say the truth table has a 1 output for A equals 1, B equals 0. This specific combination will guide us in marking the K-map accurately. We mark the cell corresponding to A equals 1, B equals 0 with a 1. This step visually represents the truth table data within the K-map framework. This process is repeated for all input combinations. By systematically filling in the K-map, we ensure that every possible state of the Boolean function is represented. This comprehensive mapping is crucial for the next steps of simplification and analysis. Once the K-map is fully populated, we can begin the process of simplifying the Boolean function. This involves grouping adjacent ones in the K-map to form larger blocks, which represent simplified terms in the Boolean expression. The goal is to identify the largest possible groups of ones, as these will lead to the most simplified Boolean expression. By carefully analyzing the K-map, we can reduce the complexity of the original function. Finally, we write the simplified Boolean expression based on the groups identified in the K-map. This expression is much more efficient and easier to implement in digital circuits, achieving the primary goal of using Karnaugh maps. In summary, constructing and using Karnaugh maps is a powerful method for simplifying Boolean functions. By following these steps, we can effectively minimize logic circuits, making them more efficient and easier to understand. Section 4. Grouping terms for simplification. The power of K-maps lies in grouping adjacent cells containing ones. These groups help simplify the Boolean expression. We can group cells horizontally or vertically, but not diagonally. The size of the group matters. We aim for the largest possible groups, as bigger groups lead to greater simplification. A group should contain 2 to the power of n cells, where n is an integer like 1, 2, 4, 8, and so on. For instance, we can group 2, 4, or 8 adjacent ones. When grouping, we look for wraparound possibilities. Cells at the edges of the K-map are considered adjacent to cells on the opposite edge. This wrapping allows for more grouping options, further aiding simplification. For example, a 1 in the top row might group with a 1 in the bottom row. Similarly, a 1 in the leftmost column can group with a 1 in the rightmost column. These wraparound groups are essential for finding the most simplified expression. Section 5. From groups to simplified expressions. Once we have formed the largest possible groups of ones, we derive the simplified Boolean expression. Each group represents a product term in the simplified expression. The variables included in the product term are those that remain constant within the group. For instance, consider a group encompassing 4 cells where the variable A is always 1, but B and C change. This group translates to the product term A. We repeat this process for all groups. After obtaining the product terms for each group, we combine them using the OR operation, symbolized by a plus sign. This combination gives us the sum of products, or SOP form of the simplified Boolean expression. The resulting expression will be simpler than the original. It will have fewer terms and variables. This simplification is the primary advantage of using K-maps. It translates directly to a more efficient digital circuit implementation. Section 6. Importance of K-maps in computer science. K-maps are not just an academic exercise. They have significant practical implications. They are crucial in computer science, particularly in digital circuit design. Their ability to simplify Boolean expressions directly translates to more efficient circuits. In digital systems, every logical operation is carried out by logic gates. These gates implement basic Boolean functions like AND, OR, and NOT. A complex digital circuit may require a large number of these gates, increasing cost and complexity. By simplifying Boolean expressions, K-maps reduce the number of logic gates required. Fewer gates mean less space on the circuit board, lower power consumption, and faster operation. This optimization is critical in modern electronics, where miniaturization and efficiency are paramount. Moreover, simpler expressions are easier to understand and troubleshoot. This ease of understanding is invaluable during the design and debugging phases of complex digital systems. K-maps make the design process smoother and less error-prone. Section 7. Modern applications of Karnaugh maps. The applications of K-maps extend far beyond the classroom. They are actively used in various fields today. From the design of microprocessors to the development of control systems, K-maps play a crucial role. In digital electronics, K-maps are instrumental in designing logic circuits for a wide range of applications. They are used in everything from simple controllers to complex microprocessors. Their ability to optimize logic functions is essential for efficient hardware design. Telecommunications heavily rely on K-maps for designing digital signal processing or DSP algorithms. These algorithms are crucial for transmitting and receiving data efficiently. K-maps ensure that these algorithms are implemented with minimal hardware complexity. Furthermore, K-maps find applications in areas like control systems for industrial automation and robotics. They help design efficient control logic for complex systems, ensuring smooth and reliable operation. In conclusion, Karnaugh maps are a powerful tool for anyone working with Boolean algebra. Their ability to simplify complex expressions visually makes them invaluable in digital design, impacting various technological advancements we rely on daily.